Let's look at a line tangent to our curve at point P. So that would be a line that looks something like this. That's the tangent line at point P. Now, as you've seen earlier, as point Q gets closer and closer to point P, the vector constructed between the origin and point Q becomes more and more parallel to the tangent line. With this, it's natural for us to now define a tangent vector tangent to the curve at point P. Now, what is this tangent vector? It's just simply the derivative of our vector function. And this tangent vector, you could also equivalently just call it the velocity of our curve. In short, our tangent, a vector tangent to a curve at a particular point, is equal to the derivative of our vector function evaluated at that point. We now know that a vector tangent to a vector function at a point in space is equal to the velocity of that vector function. Okay, again, what does that velocity mean? Well, all that is the rate of change of the vector function with respect to the parameter t. If we draw our arbitrary curve representing a vector function, this curve is curve r of t. Being a vector function, it's parameterized and therefore has an orientation. We have seen that a point on the curve, point P, has a tangent vector that can be given by the derivative of the vector function with respect to t. It is often useful to talk about the direction of a curve at a particular point in space. Now, that direction of the curve can be given by the velocity of the curve, the tangent vector, if you will, for the curve at that point. But oftentimes, we just want the direction. And the reason is, when we deal with the direction of a vector function at a point, we could then begin to explore other mathematical operations, such as how curved is our curve at a point? Is it very sharp, or is it kind of like a flat rolling hill? Well, with that said, looking at the direction of a curve at a point in space, it is often more convenient to look at a unit vector that is parallel or tangent to the curve at that point in space. Now, that unit vector, it would be natural for us to use the tangent vector as a basis of our unit vector that is tangent to a curve at a particular point in space. So let's define a unit tangent vector in terms of our tangent vector. Let r vector equals a function of t for the I component, a function of t for the j component, and a function of t for the k component be a smooth parameterized curve for the interval from a to b. The unit tangent vector for a particular value of the parameter t is given by t hat as a function of the parameter t is equal to the t vector divided by the magnitude of our tangent vector, which is just the derivative of our position function with respect to the parameter divided by the magnitude of the derivative of our position function with respect to the parameter, which is just simply the velocity of our curve divided by the magnitude of the velocity of our curve. We could define the unit tangent vector in each of these ways because each of these expressions is equivalent to every other expression. This unit tangent vector is a vector of magnitude 1, and its direction is the direction of the tangent vector which lies along the tangent line at any point on our curve defined by the vector function r. Suppose we have a vector function that can be described by this curve. And we want to look at the unit tangent vector at various points along this curve. Well, the unit tangent vector, remember, is a vector of magnitude 1 that is tangent to tangent lines at each point on the curve. So each of these unit tangent vectors that I've just drawn represents a vector that is tangent to the curve at that point. Notice how it indicates the direction of the curve at that point. So we can say that the unit tangent vector gives us the orientation of the curve, telling us the direction in which the curve is evolving in response to the parameter t. Earlier, we said we could interpret the tangent vector as being equivalent to the rate at which the position vector on the curve changes as a function of the parameter t. Using a physical example, this would correspond to the velocity of the curve. Not that the curve is moving in space, but rather it represents the rate at which the curve is changing with respect to the parameter t. Now, since we define the unit tangent vector as being the unit vector in the direction of the tangent vector at any point on the curve, and since the tangent vector is just the velocity of the vector over the magnitude of the velocity of the vector, by rearranging this definition of the unit tangent vector, we could say that the velocity of a curve at any point is tangent to the curve at that point. This is a very useful result that extends to physical phenomena because it gives us a mathematical expression that shows how the velocity of an object is tangent to the path at which that object is traveling. Now here we have a mathematical point on the curve, but this point always remains on the curve. And we could say that the rate at which this point is changing along the curve with respect to the parameter t corresponds to its velocity on the curve. And notice the velocity at every point is tangent to the curve. Therefore, we can say that velocity is tangent to the position curve at each point.